Question 60 moves the focus on energy transfer away from fluids and onto equipment. The concern with this question isn't so much balancing energy between water and refrigerant, but rather on using the attributes of a heat exchanger to derive energy transfer. Initial critical thought solution elements. 1. What are you solving for? Refrigerant mass flow rate through a heat exchanger. 2. What is the fundamental process? Heat transfer by way of machine properties. 3. What are the first considerations to find the solution in connection to the fundamental process? Determining the appropriate change in temperatures for the only possible solution path. 4. Are there key assumptions? Ideal effectiveness of the heat exchanger. This video is brought to you by ExOverZero, which offers the best HVAC PE study material possible. Want to pass the test? Buy the books. Use the link below to purchase. The most tempting first path to solution is attempting to balance the energy moving out of the refrigerant with the energy moving into the water. The heat exchanger on the condenser leg is doing just that, exchanging heat. It takes heat in the form of enthalpy, out of the refrigerant, and puts it into water in the form of temperature. The refrigerant is the hot fluid being cooled, and the water is the cold fluid doing the cooling. As is overwhelmingly the case with HVAC&R systems questions, begin with energy flow in order to find a solution path. Energy flow occurs in units of BTU per hour. There's a refrigerant flowing at an unknown rate of pounds per hour, which loses enthalpy, or BTU per pound. The question gives the enthalpy data. Pounds per hour times BTU per pound equals BTU per hour. You must determine this value to answer the question, and you're not given this value. One equation, two unknowns. More data is needed to solve it. Perhaps this energy flow can be found by determining the energy flow in the water and setting them equal. The energy flow equation for water must be memorized for the PE. Don't waste time looking this up. It's this. The question gives the temperature data, but the volumetric flow and energy flow are unknown. Again, one equation, two unknowns. Using pure critical thought, see what other variables are available and begin to assemble them by unit analysis. There are pressure and temperature variables for the refrigerant, but those don't connect to any other variable in a meaningful way. But there is a heat transfer coefficient for the heat exchanger in BTU per hour feet squared degrees Fahrenheit, and also the heat exchanger's surface area in feet squared. These have a unit in common. And once that's canceled out by multiplication, all there's left to find energy flow in BTU per hour is to cancel out the degrees Fahrenheit by multiplication. So, where is a temperature delta for this? In the water, right? It's tempting to use 75 minus 60 for the temperature value and solve. But there's another temperature given in the question, the refrigerant temperature. And there's technically a temperature delta for the refrigerant. It's 0. But there's still a beginning and ending temperature value. Between saturated vapor and saturated liquid conditions, any process, like that of the condenser in this case, which is at a constant pressure, is also at a constant temperature. So it should be just as tempting to use 140 minus 140 for this temperature value too. But obviously you can't use both, at least not in the context of energy flow within the fluids. Consider that the question uses the heat exchanger's properties of surface area and heat transfer coefficient. So keep the focus on that piece of equipment to find the temperature delta. A counterflow heat exchanger can be diagrammed like this. The refrigerant flows in one direction. The water flows in the other direction. Hence, counterflow. Because these are two different fluids with different properties, such as density, both the temperature and enthalpy changes don't match. The energy flow in the massless unit of BTU per hour does match. Energy flow that goes out of here must go into here. The only remaining option critical thought leaves is to consider that there's a special temperature delta for heat exchangers. But it's something that must be looked up. It's called the logarithmic mean temperature difference, LMTD. Find it in the NCEES Mechanical Reference Handbook in Section 5.5.3. Now, while this formula was derived from critical thought by the HVAC engineering community, it's highly unlikely that you'd think to yourself, if I need to find the temperature delta of this heat exchanger, the best bet is to consider a logarithmic mean of the 4 fluid streams. So, understand before you go into the PE that there's a unique way to calculate temperature deltas for heat exchangers. You just gotta know that, and at least have that fact memorized for the PE. The LMTD is extremely likely to appear in multiple PE questions, and heat exchangers are very commonly analyzed in the exam. So, in the list of things to have memorized for the PE, make sure this makes it on there. Also, be able to quickly find it in the reference handbook. Putting the LMTD into this equation from earlier, here, gives the energy flow at the heat exchanger. As was said earlier, the energy flow matches for both the refrigerant and the water. So, use it to supply one of the 2 missing variables in the refrigerant flow equation, used when first looking for a solution path to this problem. This equation is therefore populated with the appropriate data. And solving for fluid flow gives roughly 193 pounds per hour. Option D. To get good at questions like this, you should be able to quickly reference the NCEES Mechanical Reference Handbook to find things like the LMTD. You can't do that by just reading through it like a novel. Get good at it in the only way possible, by practicing lookups in it. To do this, ExOverZero has a one-of-a-kind drill book for the NCEES Mechanical Reference Handbook. Use the link below to purchase.